Well, thank you for your introduction. And good afternoon. And I'm Chen Koluo from Tulane University and Wuhan University. And I'm very glad to introduce my work here today on execute-only memory, or XoM. And our paper is titled Retrofitting XoM for Street Binaries Without Embedded Data Relocation. Let's just jump into it. First, I want to introduce what is just-in-time oriented program is, or JIT-ROP. In JIT-ROP attacks, attackers exploit memory disclosure vulnerabilities to dynamically disclose the code pages of a running program, and then traverse the code pages and search for required gadgets dynamically, and then use a JIT-ROP compiler to compile the identified gadgets into payload, and then use a control flow hijacking vulnerability to finally compromise the target machine. So why do attackers need JIT-ROP when they already have the regular ROP? So in a regular ROP, the attackers must have the exact same binary running on the target machine. And the attackers use the disassembly and searching for the gadgets offline, and then chain the gadgets into payload before launching the attack. However, ASLR randomized the code base address and the previous found gadgets, the position of previous found gadgets will be changed. So the attackers won't be able to use the previous found gadgets again. However, the ASLR is a coarse-grained randomization, and it only randomizes the base address of the code. So it is very easy to bypass. The attackers can use the techniques like return to PRT, pointer leaking, and partial pointer override to bypass the ASLR. To further enhance the ASLR, fine-grained code randomization was proposed. Fine-grained code randomization randomizes the code at the function or basic block granularity, so the entire code layout will be shuffled. And this is where JIT-ROP comes in. With the JIT-ROP, attackers use the memory disclosure vulnerabilities dynamically disclose the randomized code layout, thus breaking the secrecy promise of fine-grained code randomization, making the randomized code layout transparent to the attackers again. So when talk about defending against JIT-ROP attacks, so naturally we'll think about to restrict the attacker's ability to disclose the code, and this method is called execute-only memory, or XoM. XoM disable the code, the read permission of code pages, so the attacker won't be able to read the code page and to defend the JIT-ROP attacks. However, in reality, the code pages may contain some embedded data. If we disable the read permission of the entire code page, the legitimate embedded data reads will also be blocked, and when the program trying to read this embedded data, it will crash. So the current binary-based XoM trying to solve this problem by using disassembly and binary rewriting techniques. They use the disassembly to identify all embedded data and trying to use the binary rewriting technique to relocate the identified embedded data to standalone read-only areas. However, as we all know that the precise distinguish of code and data is an inherent challenge of disassembly. So there may be a code to embedded data misidentification and embedded data to code misidentification. For example, in the case of the upside, there are 4 embedded data are misidentified as an instruction. So when relocating the embedded data, these 4 embedded data bytes will be remained in the code page, and the code page will be unreadable. So when the program trying to read these 4 bytes of embedded data, it will be blocked and the program will crash. And on the other hand, if there are an instruction that are misidentified as embedded data, for example, below here, in this case, the misidentified code will be mistakenly removed to a standalone read-only memory block. And when the program reaches this point, the program will crash. So imagine there is a memory permission control mechanism that implements a fine-grained read permission control that allows you to manage the different read permissions of different memory blocks within a code page. There is also the disassembly approach that can completely avoid embedded data to code misidentification while tolerating a relatively high rate of embedded data to code misidentification. So we can allow all the data reads targeting to the identified embedded data while disabling all the readable permissions to the code areas. So with this setup, we can protect the code from the attackers while tolerating the legitimate embedded data reads. So you may ask, there are some code to embedded data misidentifications. Will it cause any problem? The answer is no, because the misidentified code still have the executable permission. So when the program executes to this point, the code is still executable, so it won't cause any problem. So I'm going to introduce the overview of PXoM. Given the binary file as input, we firstly perform unidirectional disassembly, which I will introduce later. And after the disassembly, there is a protected binary file. The protected binary file will be generated, and the identified embedded data list will be attached at the end of the ALF file. And then when loading the protected binary file, the custom loader in the kernel will firstly load the embedded data list. And then the exception handler will start to monitor all the code page reads. And when a code page read comes in, the exception handler will check if the target is in the embedded data list. If it is, it's a legitimate embedded data read. If it is not, it will be treated as a code disclosure attempt. So as you can see, the embedded lists are separated into two lists, and there is an optimization list. So we build a special optimization policy to accelerate the read of the high-frequency embedded data read scenarios. So for the time constraint, I won't introduce it here. Please refer to our paper for details. And I'm going to introduce the unidirectional disassembly, as I mentioned earlier. The purpose of the unidirectional disassembly is to identify the embedded data while tolerating some misidentified code as embedded data. So I will use this case as an example to demonstrate how unidirectional disassembly works. On the left side is a code page is the ground truth of a code page containing some embedded data. So in its initial state, we treat the entire code page as the embedded superset. This superset contains all embedded data and the misidentified code. So we firstly employ the recursive traversal disassembly from the program entry point, and this will generate the result C. However, if we only use the recursive traversal disassembly from the program entry point, you will cause approximately 49% of code miss, which is unacceptable because it will expose too much code to the executable and readable code to the attackers. So we find additional code entry points using for example, the jump table entries, the address taking functions, and the unwind information. And then we use recursive traversal disassembly from these additional code entry points, so to further minimize the embedded data superset. To assess how PXoM can provide how security PXoM can provide, we proposed two metrics: code coverage and overall coverage. The code coverage reflects the proportion of protected code from all actual codes, and the overall coverage reflects the proportion of protected memory from all executable memory. For the open source programs, our average code coverage is 97.07%, and the average overall coverage is 95.29%. And for the open source programs, since we cannot obtain their ground truth, the overall coverage, we report their overall coverage, and the average overall coverage is 96.94. For the performance evaluation, we use the Aaron bench to assess PXM's performance evaluation. And for most of the tasks, it causes negligible overhead. However, on the most right side, we can see that it causes 3.2 times of performance overhead, which is reasonable, which makes sense because when determining the code page checks, the kernel must iterate through the embedded data list, and to allow the embedded data list, the kernel must perform a series of operations to allow it to happen. However, the overall coverage of PXOM is very, very low. The average overhead of spec CPU 2017 is 0.36%, and the geometric mean is just 0.25%. To further investigate how it caused such a low overhead, we proposed a metric called read identity, which reflects the frequency of embedded data codes of the programs. We can see that even for the highest read frequency happened in OpenSSL, it still takes millions of instructions to perform just single one embedded data read. In conclusion, current binary-based XoM requires relocation of code and data. However, precise separation of code and data is an inherent problem. PXoM retrofits XoM for strict binaries without embedded data relocation, and the performance loss of PXoM is negligible. Thank you.
Speaker. Questions from the audience? Please state your name and affiliation.
Hello. First, amazing work. Alexis Vulmaneas from TU Delft. So when I was reading your paper, I saw your kernel components, and I somehow thought that some of these functionalities can actually happen using only user space techniques. Did you try to do it only using user space and you find problems there, or you immediately try to do it using the kernel components?
Thank you. That's a good question. So if you use only the user space to solve this problem, there are some. Let me show you this overview. As you can see on the right top of this figure, there are some data structures like embedded data lists, and these structures must be protected in the kernel space to avoid temperature. If we put it in the user space, the attackers may attempt temperate these data structures. For example, they can add whatever they want to read into this embedded data list because they have the ability to temperate the user space memory. So this will cause some security problems. So we use the combination of user space and kernel space.
Okay, thanks a lot.
Time for one short question, which I'm going to ask. So thanks for this talk. I enjoyed it. I was wondering, so if I get it right here, this assembly mechanism allows you to have, you will grant still some accesses to some code. This leaves you with some residual attack surface. And can you find gadgets in there? I suppose you evaluated this in the paper. I mean, like the fact that you don't break the program, but an attacker may still read that code, right?
Yeah.
So can an attacker abuse that?
I'm sorry, I don't think I quite understand your question.
Yeah, I mean, I'm saying that to identify which are the valid data and then allow these accesses to valid data, you also have some code in there, right, as a false positive. So an attacker can still read some code.
Yeah. The attackers can still read some of the misidentified code. Mm-hmm. So naturally, we'll think there may be some security problem if the attackers can read some of the code. However, As you can see, the results of our unidirectional disassembly, the code coverage reflects the protected code, the proportion of protected code from the real code, and it reaches 97.07%, and only approximately 3% of code is exposed to the attackers. So I think it's safe enough to protect most of the code and expose some of a little portion of the code to the attackers.
Yeah, so it's this 3%. It's unlikely that they find enough gadgets.
Yeah,
Yeah. Thanks a lot. And let's thank all the speakers again and enjoy the next session.